All right, folks, this is part 2 for rotational kinematics. And this might sound a little bit like a math lecture, but please don't zone out. I think the more you understand what the definition of theta is, the easier some of these equations will be, the easier it'll be for you to check your work. Okay, so fundamental definition of radians. Theta is arc length, which is the variable is s, over the radius of the circle. So this is the arc length s, and if you take that number, because if you took a piece of string and measured that distance and laid it out on a ruler, that's a length. If you divide it by the radius, this is dimensionless. Oh, I had it right there. Okay, that is the definition of radians. Okay, let's make sure that makes sense, because you don't get this equation on the AP sheet. Okay, so what we're going to do is we're going to change each variable. Let's keep r the same. So I have two circles of the same radius. I'm going to have a tiny arc length. Let's see, I think the peak will show better. I have a tiny arc length s, and that results in a small theta. I have a big arc length s2, and that's a bigger slice of the pizza. That's a bigger theta. And it's not obvious that it is directly proportional, but at least it's bigger, right? So that's why s is in the numerator. If s goes up, theta goes up. It's directly proportional. Okay, now we're going to keep the arc length the same. So imagine I have the same piece of string, and I see how much of the pizza that if you have a big pizza, and I'm like, okay, your slice of pizza, I'm gonna put this string along the pizza, and that's the slice of pizza you get. You can see that clearly this is, I think, still more pizza, but the angle theta is 90 degrees here. It's 1/4 of the pizza, yay. So in terms of the percent of the pizza you get to eat, yay, you're happier for this pizza than you are for this pizza, right? So theta, when r went up, because it was in the denominator, theta went down. The percent of the pizza that you get for that particular arc length goes down. Okay, so I hope that this makes sense for you. Okay, so if you solve that relationship, the fundamental definition of theta, if you solve that for arc length s, then you get s equals theta r. How we will use this in physics is you might use rotational kinematics to find the theta through which something traveled. So I don't know why the position function wasn't on the slide deck. Maybe because I was too lazy to make this with LaTeX. But anyway, maybe you do, you use the position function to find how many angles and radians the bicycle wheel went through. Okay, but you didn't really care how many. And this is what your odometer does. There's a little piece of, there's a magnet, and each time the magnet goes by your odometer, it'll count 1 rotation, 2 rotations. So maybe you don't care about the number of rotations. Maybe you care the actual distance you traveled on your bike. That's why you would use this. You would say the real distance I traveled on my bike is the thetas that my bike wheel went through times the radius of my bike tire. Okay? But it just comes down from the definition of theta. All right, this is the formula we will actually use a lot. If you take the derivative of arc length equals theta times r, the derivative of the arc length is your tangential speed. It is how fast that LED is traveling in terms of moving through space. Okay, so that's a distance. The derivative of that's velocity. R is constant. The LED isn't changing its location relative to the pivot. Okay, it could, and then you have to use the product rule. I know how to do the calculus. I just sometimes forget the words. You'd have to say plus theta dr dt. Okay, so if you take more physics in college, you might see that term. We're not going to do that. So we're going to say R is constant, but the derivative of theta is omega. Okay, this is a super important relationship. It is the derivative of the definition of radians. And just to reinforce this, and then we'll do the example problem, this is what we figured out at the start of the slide deck. Point Y, if you double R, then you double the speed, because if you're twice as far away from the pivot, then point Y has to travel twice as far. I don't think this is twice, but you know what I mean, to get around once as point X does. So it's got to be moving twice as fast. Okay, so super important relationship. Hope that makes sense to you. All right, so we will do an example problem, and then we're done. So you can read this while I'm changing pens. Okay, I don't know if you know centrifuges. You can put like blood in there and separate the platelets or whatever. It's rotating at an angular speed of really fast, and then it's switched off, and it goes through 50 revolutions before coming to rest, and we want to find constant, because otherwise the formulas don't work, angular speed alpha of the centrifuge. Okay, so I chose this problem because we first need to convert. This is in revolutions per minute. Those are not the right units. So omega is 3,600 revolutions per minute. We'll do the easy one first. 1 minute is 60 seconds. And 1 revolution is 2 pi radians. Okay, multiply all the numerators, divide by the denominator, and you get pretty much 377 radians per second. That is omega naught. Okay, then also kind of annoying, it goes through 50 revolutions. Okay, that's also not the right units. So start with 50 revolutions. 1 revolution is 2 pi radians. So that's 100 radians or 300, sorry, it's 100 pi radians or 314 radians. Okay, now we are ready to practice. Theta naught is 0. Theta final is 314. Omega naught is 377. Omega final is 0 because it came to rest. We care about alpha. We don't know or don't care about time. All right, so we're going to use don't know, don't care, but we're going to use all the new variables. Okay, it came to rest, so that is 0. This is 377. We're looking for alpha, and it went through. Now notice it didn't say clockwise or counterclockwise. We're just assuming, we don't know. It doesn't really matter. Whatever the direction it is moving in is alpha is going to be opposite that direction. Okay, so what you get is this squared brought to the other side is 142,129 equals 628 alpha, multiplying these two things, and that gives you an alpha of minus 226 radians per second squared. I will tell you right now, super quickly, almost done. I really don't, I need to make a chart with some known rotational speeds of stuff like the Earth or something. Anyway, I do not have a good sense of what radian per second is or radians per second squareds are in terms of what's reasonable. 3,600 revolutions per minute seems pretty freaking fast, right? So anyway, I'm just being transparent that when you do, so if I make up the problems, the equations are going to be right. I don't know if the numbers are going to be realistic. All right. Thank you for listening, and I will see you in class.